Hello, everyone. Welcome to another ASEG Tech Talk. Today, I have the pleasure of introducing Caroline Eakin. She will be giving a talk on unveiling the Gawler Craton, new insights from passive seismic deployments in South Australia. Caroline is a seismologist and a senior lecturer at RCS at ANU. Caroline did her PhD in geophysics at Yale University. Following her PhD, she held a postdoctoral fellowship at the University of Southampton at UK. She joined ANU as a faculty member in 2016, and she was awarded a DECRA fellowship from the Australian Research Council in 2019. In 2022, she received the Outstanding Early Career Scientist Award in Seismology from the European Geoscience Union. Before we start, I would like to acknowledge the traditional custodians of the country. The ASEG acknowledges the traditional owners of the land on which we gather today and the many lands on which we undertake our work. We recognize their continuing connection to these lands, water, and culture, and pay our respect to their elders, past and present. Thanks to our corporate members and our branch sponsors for their continuing support. And just a little housekeeping, if you are joining us on Teams, please turn off your microphone so that there's no interruption during Caroline's talk. If you have any questions, please pop them in the chat. We will go through them at the end of the talk, and we will have a Q&A session at the end. Just going through some of the benefits, if you decided to become a member of the ASEG, you get free access to the exploration geophysics, access high-quality research results and relevant case studies in the ASEG Technical Journal, a free copy of the preview, which keeps you stay up to date with current trends in exploration geophysics. You get a reduced entry to AEGC conferences. You get a free entry to regular technical events in your state. Access to job advertisement posted on ASEG websites, and access to annual wine offer. Get that too. Social events in your states, and we're trying to foster a professional network by connecting with generous professional networks with wide experience. And you get we have research funding and travel scholarships for students as well. You also get a free our membership is free for students and half price for retirees and recent graduates. And please make sure that you follow us on social media. And with that, I hand it to Caroline.
Thank you very much for that. Thank you all for joining in person and online. It's really exciting to have the opportunity to talk a bit more about my research. And this is the first time I've given a talk at GA in this building, so I'm very excited about that. And I'm going to be talking a bit about research that since I came to Australia, I've been working a lot in South Australia as passive seismic deployments there. I'm going to share some of the research that we've been doing over the past several years. We're going to be focusing on the Gawler Craton. And the first question for perhaps some of the non-specialists in the room is, what are cratons? The cratons are the oldest building blocks of continents. We look here at a cross-section through the crust and upper mantle. We see that the cratons here formed in the Eakin are the regions with the thickest lithosphere, the thickest part of the continent. And they're the parts that have been at the Earth's surface for the longest and moved around since many billions of years. They've survived the longest amount of time. If we look at in time, from the Earth's evolution from magma ocean to present day blue planet, then cratons assembled and stabilized in this time period, essentially close from the start of the Earth, 4.6 billion years ago, up to about 2.5 billion years ago. So cratons were forming before the rise of oxygen, before the rise of complex life. And they've basically then moved around the Earth's surface since then in the plate tectonic cycle. So they're important because they give us a window into ancient Earth, into the evolution of Earth, but they're also regions of economic importance as well. So here is, we look at cratons, location of cratons globally. In pink here is where we have cratons, cratonic areas, and they often form the core of our continents. Continental material is assembled around these cratonic cores, underlain in these regions by thick lithosphere. And on this map here, Mark, can you see? Do we have a pointer of any kind? I use my hand. Can you see? Yeah, I can do that.
But they can't see it online.
They can't see the line.
There should be a pointer on the PowerPoint.
There's a mouse, but it's not coming up on the screen there. It's so on this map here, colored dots represent some globally significant mineral deposits, gold, copper, nickel, diamonds, and these are often associated with these cratonic regions and often on the margins of these cratonic regions. So they're important because they tell us about the evolution of life, and they're also important economically in terms of our minerals. Something that's a more field in its infancy, but something I've started to get interested in, and I'll touch on more later, is about natural hydrogen. And I believe there was an ASEG tech talk about that a couple of talks ago as well. And cratons are important regions in the world for this as well. So there's a lot of interest at the moment in hydrogen as a clean energy source for the future. I'm just gonna leave.
Oh, so it is. Oh my God, it doesn't show up on the screen.
Yeah, so there's a lot of interest in hydrogen as a clean fuel for the future. We can make hydrogen in different ways, but a lot of interest right now is also trying to search for places where hydrogen might accumulate geologically or naturally. And one of the sort of places on Earth is on cratons are potentially good places for natural hydrogen for a couple of reasons. There's many different ways that hydrogen could potentially be produced. One is which oxidization of iron-rich rocks. So in our cratonic areas, we may have some banded iron formations. Also in radiolysis, so where we have rocks such as granite and gneisses, which are rich in radioactive minerals. That radioactive decay, as part of that process, interaction with water, can also produce hydrogen. So in this map here from recent paper, in grey, dark grey, are the cratonic regions, and highlighted colored symbols are different observations of natural hydrogen or hydrogen seeps emanating from the Earth. And we see that several of these, or many of these, are associated in these cratonic regions. So the crystalline basement of cratons, fractured basement, people are starting to associate maybe regions that we're interested in to go explore for natural hydrogen. So looking at Australia, where are the cratons? And Australia, as most people are probably aware, is composed of three major cratonic regions: the North Australian Craton, the West Australian Craton, and the South Australian Craton. So these regions, this western 2/3 of Australia, is underlain by thick lithosphere. So on the right, we have a map of lithospheric thickness from the OSRAM seismological reference model. In blue, darker the blue, the thicker the lithosphere. So we see that the western 2/3 of Australia is underlain by 200 kilometre plus thick lithosphere, whilst the eastern Phanerozoic Australia is underlain by maybe 75 thick. So on the left, we have in different colours showing different Archean and Proterozoic provinces together, showing different Precambrian units that have exposure at the surface. So we have this sort of geological divide in Australia, the older western part and the younger eastern part. But we'll see that these provinces shown, these are parts which are well exposed at the surface. Likely the areas in between are also underlain by old lithosphere. We see the lithosphere is thick, old cratonic material, but is covered by sediment and not as well exposed. These lines are dashed. We don't necessarily know the boundaries where these cratonic elements are as precisely as shown. The focus of this talk and work that I've been doing the past several years is looking at the South Australian Craton and the Gawler Craton in particular. The Gawler Craton is one of the oldest building blocks of Australia, centered upon an Archean core with a Paleo to Mesozoic, Proterozoic regions around it. To the east of it, we also have the Curnamona province. It's not shown on the geological map here, but it's also another thought to be cratonic element. But the core of the South Australian Craton really focuses around the Gawler subcore component. There's different provinces within it. We can see in black lots of different faults and shear zones. The Craton hasn't always been strong and undeformed. It's gone through periods of deformation. And in red and purple in the center here, we have the Gawler Range volcanics in purple and the Hilltalbus Tweet in red, periods of extensive volcanism that affected the Craton about 1.6 billion years ago. That was the last period of major deformation, and since then it's stabilized, cratonized, and remained relatively strong and stable since then. So we have knowledge here of the Gawler Craton, mostly where rocks are exposed. We have this outline that's shown a lot, but again, this outline is basically where we have information. We don't necessarily know the boundary of this Gawler Craton exactly well. The Gawler Craton is important to be shown globally. Cratons are important for mineralization, and that's true as well for the Gawler Craton, and in particular the eastern margin of the Gawler Craton. So these margins on the eastern side of the Gawler Craton, here is just showing an example for copper in green. We have many different copper resources and occurrences along this eastern margin. And I was quite struck making these maps on the left here with the seismicity. Craton margins, because the cratons themselves are strong crust, a lot of the deformation, seismicity, earthquake activity gets focused on the margins, the weak zones. So today we have the Flinders Ranges uplifting. We have a lot of seismicity, one of the most seismically active parts of Australia. We have seismicity along the eastern Eyre Peninsula. And we have this band of seismicity that goes up to the southwest of Lake Eyre that seems to kind of follow this trajectory of the margin of the Gawler Craton. I don't have an answer for it, but also interestingly, I think it's the third largest recorded earthquake in Australia. It's a magnitude 6.4 in the Simpson Desert in 1941. This is an area of very thick sediments, and we have very little information about what causes this large earthquake and continuing earthquakes that continue to happen there in recent years. As well as the copper that I showed previously, I talked about its interest in cratons for natural hydrogen. That's also true for the Gawler Craton in South Australia, is quite interested in this hydrogen. On the left is showing occurrences of uranium, which could be potential for radiolysis sources of natural hydrogen. And on the right is occurrences of iron, particularly in the Eyre Peninsula and up in the Olympic Dam province. We have iron deposits and occurrences, and these iron, when we have oxidization of this iron at depth, could also produce natural hydrogen. So it's quite a rich area in many different ways. And South Australia, I believe, was one of the first jurisdictions to open up exploration licenses for exploring for natural hydrogen. So on the left here is figure from 2022 showing all the license applications. They opened this up in 2021. These are all the different license applications for natural hydrogen. We see quite a bit eastern Gawler margin. And there's two at this time that have been granted in solid yellow along the York Peninsula and Kangaroo Island, a company called Gold Hydrogen, and in solid blue here, a company called H2EX. And recently we've been working with H2EX in this region, in the Gawler Craton. We're partners on CRC project, Cooperative Research Centre project, H2EX and the University of Adelaide, who've been doing MT work and surveys. And we've been out earlier this year deploying arrays of nodal seismometers. And I'm actually heading into the field again on Saturday to put out some more. So we've been working in this region to better understand the crust of the Gawler Craton. We're working at a much smaller scale, and this is stuff that's ongoing, but it's one of the interests in this area. But that's not the focus of what I'm going to talk about today. I've been working the past few years on a much broader scale over the Gawler Craton. So the map on the left here now shows all the symbols, show places where we put passive seismometers, either short period or broadband seismometers. These operate for a year or more at a time, and they can study the deeper parts of the Earth from the crust into the lithosphere and the upper mantle. And up until about 2016, when I arrived in Australia, there had been very few seismometers placed relative to other states, let's say. There had been few seismometers placed in South Australia. But starting in 2017, ANU deployed the blue diamonds. Then we had the Marla line, which was a dense line across the top of the Gawler Craton. Then I led deployment of the yellow symbols of the Lake Eyre Basin seismic array. And then in white, at the same time as the Lake Eyre array, the Geological Survey of South Australia deployed what they called the ASEG essay. So we had these two deployments out at the same time, and we collaborated together, and we got then a much better coverage of the eastern Gawler margin. So using these data sets is what I'm going to present some of the results of today. One of the reasons why we did this, why we're putting out these seismometers, is this importance around these cratons and these craton margins, but they're not always so well defined. So on the right, we have a map here of different sedimentary basins in South Australia. And this eastern part of the Gawler Craton, there's quite a few sedimentary basins, and as we go up to the Lake Eyre Basin, we have many different overlapping sedimentary basins of different geological age. And these obscure then our knowledge about these craton boundaries and craton. On the left here, it's an image people might have seen many times before of different estimates of so-called Tasman line, or essentially trying to understand where the boundary between that older Precambrian Australia might be and that younger Phanerozoic Australia might be. And in this part of Australia, in central Australia, beneath the Lake Eyre Basin, is a region where these estimates vary quite a bit. We really have, at this point in time, very poor knowledge about where that boundary might be. Okay. So our key problem is that Our geological boundaries, crustal and lithospheric boundaries, are currently hidden under sedimentary cover, such as the eastern margin of the Gawler Craton. And passive seismology is one technique that we can use to try to help address this. This is one of the goals of my ARC DECRA fellowship, and has funded then a lot of the work that you're going to see. We're interested in this margin going from the old, thick, strong Gawler Craton into potentially a weak zone at the edge of the craton and a thinner crust potentially beneath the Lake Eyre region. So at the same time that I was working on my DECRA, another seismologist, JP O'Donnell, who was at the Geological Survey of South Australia, used these data sets to look at ambient noise tomography, which gives us these really nice images of seismic velocity in the crust in this region. And as you would expect, here on the left, you see depth size at 2.5 kilometers, on the right, 15 kilometers. And this method shows really nicely we have fast seismic velocities in the Gawler Craton, blue colors. Here's the Cratons province to the east, also mostly fast velocities within these big fine provinces. And then to the northeast into the Lake Eyre Basin, where we have a lot of sediment, we're seeing slower seismic velocities. And these are some other basins as well. So this technique is really good at giving us this image of the crust and its properties, showing us where we have crystalline crust versus sedimentary basins. But tomography gives us a generally smooth image. It doesn't identify where sharp boundaries might exist. It's a bit ambiguous. We have to make some assumption if we want to figure out the depth of the sedimentary basins. We have to make some assumption about the velocities. So what I'm going to show is some other complementary techniques in addition to seismic tomography that we have that potentially tell us a bit more about sharp boundaries or interfaces at depth. I'm going to look at some results from seismicity, from receiver functions, and from seismic anisotropy. So I've got 3 parts that we talk a bit more about each of those. So the first one is the seismicity from these deployments. And for these first 2 parts, a lot of this work was done by former PhD student Shubham Agrawal, now a postdoc at the University of South Carolina, but his PhD was focused on these deployments. So with the Lake Eyre seismic array, the green triangles on the map here, he was able to detect and locate 139 earthquakes, which are the larger circles in red. During the same time period of deployment, there was 18 in the national catalogue put out by GA. So even though 139 doesn't sound like a lot, with these stations, it is an order of magnitude earthquakes. All black dots represent the historical seismicity in the region. So we had a generally sort of scattered band of earthquakes through this region. But with the new catalogue, we see that the earthquakes focus and linearize. So we think this feature here is running northwest to southeast past the Eyre. So they focus onto a more narrow band of seismicity. And when Shubham looked at the focal mechanisms, the majority of the events that he could measure focal mechanisms for in dark green were consistent with having a left-lateral strike-slip motion on this fault. So that was new information. We think we've defined by a fault system, strike-slip left-lateral, and perhaps this fault system is then defining that eastern edge of the Gawler Craton. The question is, why are we getting earthquakes in this region in particular? And we think that there's a hint from this region from the water. So there's a lot of ground springs or mound springs in this region. This is a photograph from one particular spring that I took on fieldwork. And they're being fed, water is coming from deep from the Great Artesian Basin. If we look in now of these earthquakes in red, the blue stars are mapped locations of groundwater springs. So there's a spatial correlation between where there's earthquakes and where there's groundwater springs. Great Artesian Basin exists in the north and east. The water flows from Queensland and Eastern Australia through the Great Artesian Basin and is coming up outflow in this region with these springs. So what we think is where we have this fault, we have fluid-assisted seismicity. We have water from the Great Artesian Basin that's coming up on this fault. But what's really interesting is that people previously had done some isotopic analyses on these ground springs, and they detected within these groundwater, there's gases with mantle-derived signatures in the helium ratios. So it suggests that this fault has some connection to the mantle, that not only is it what seems to be a large-scale fault system, but potentially a trans-crustal cutting through the whole crust in order to get this connection, these gases, to the mantle. So that, based on this evidence, we're suggesting that this is potentially defining that eastern margin of the Gawler Craton. Second project, Shubham then worked on looking at receiver functions. Those that may not be receiver function aficionados. Receiver functions tell us about interfaces at depth below the surface. So they look at where seismic waves come up from below, and then we have a conversion between wave types. So we might have a P wave that converts to an S wave at an interface or a boundary where we have a difference in seismic velocity. So we use these a lot to infer the moho, the boundary between the crust and the mantle. But we can also use them to look where we have sedimentary basins to look at the interface between the crust and the sediment, where the sediment is lower velocity. And on the bottom here is our corrected receiver function. We see a big pulse here, which is our sediment crust signal or interface, and a smaller pulse here, which is our crust mantle moho signal. Problem with sediments, though, is these waves get trapped in the sedimentary layer, and we get these strong reverberations. So they often make analyses, receiver functions, quite difficult to map the moho. We get this kind of ringing, this sinusoidal signature in the receiver function. But if we know something about the depth of the sediments, we can do different methods to estimate that depth or thickness of sediments. We can then predict this sinusoidal reverberation signature, and we can correct that from the receiver function to get a more clean version that shows us the signal that we want to see. So Shubham worked on a couple of these different aspects. One of the first things he did was actually looking at the delay time in this first arrival on the receiver function, and that's related to the sediment thickness. So he used that in conjunction with borehole database to calibrate these different time delays to then predict the sediment thickness across South Australia using the seismic information as well as the boreholes. Here, the triangles are the prediction from receiver functions. So we see in pink, very little sediments over the South Gawler Craton. As we go up to the northeast, the Cooper and Eromanga basins, we have very thick sediments in this northeastern corner of South Australia. Once we had information about the sediments, we could then correct those to look deeper at the moho, those corrected receiver functions. Shubham's results here are shown in these larger circles. The triangles are past active seismic surveys, and the little squares are estimates from past passive seismic surveys. So there's a lot going on in this image. It is quite complicated, particularly up in the northeast where there are those sediments. But what we did find was generally brown colours, kind of consistent depth over the Gawler Craton. Then, as been seen previously, in these active lines, we go to blue colors, having some thinner crust, brown again, thicker, potentially thinner again up here. There's not a clear definition change in thickness with the edge of the craton, but we do generally, with these stations, go to blue colors, thinking that we have a thinner crust beneath the Lake Eyre region and a thicker crust beneath. The simpler way to look at it is with these violin plots. We have different regions on the bottom. In blue are the results from Shubham's study, and in the beige colors are previous results from reflection seismic studies. And what we find is that the Gawler Craton is generally thicker, sort of about 40 to 45 kilometers thick. Musgrave province, another Proterozoic province, is probably similar, but the Lake Eyre region seems to be thinner, about 40 kilometers thick. But this is also similar to the Cernamona province, which is another Precambrian province close by within the South Australian Craton. It does seem that there is a difference between the crust of the Gawler Craton and that beneath the Lake Eyre region, but it's not actually as thin as previous people had suggested. That's rotated for some reason. I've edited it. Right our heads here. But the Osmoho model, which is a crustal model for Australia, when I first came to Australia around 2016, the image was like this. And what, even though it's sideways, you can see that in the center of Australia, there's this lighter patch where it was being proposed that there was almost a hole in the crust only 30 kilometers thick, right next to some of the thickest crusts in Australia. So this is one of the motivations to see if this is real, because there was very few measurements in this region actually constraining it. And as we saw earlier, the sediments is hard to constrain it. We moved to 2023, and Brian Kennett led a new compilation or update to the Osmoho model that now incorporates our results from the Gawler Craton and Lake Eyre region. And we see that we still have this thicker crust over the Gawler Craton, going to thinner to the northeast of Lake Eyre, but it's not as dramatic as that change in the previous. Okay. The last part is to talk about seismic anisotropy, which is one of my favorite topics. And I think it's something that has been something that's very useful to understand about the upper mantle, subcontinental lithosphere, but something that's probably been, I'd say, up until recently, overlooked quite a bit in Australia. So what's useful about anisotropy? The seismic anisotropy, first of all, defines a difference in seismic velocity with direction. An example of this is olivine crystals. These form a primary component of the upper mantle. In green, these crystals, seismic waves travel fastest along the A-axis and travel slower along the B-C axis. And it just so happens that when you deform olivine aggregates, such as the upper mantle or the asthenosphere, then that shear direction, that deformation, will tend to align these fast directions, these fast crystal axes in that shear direction. So seismically, if we can measure the fast direction, we can infer something about the direction of flow and the patterns of deformation in the Earth's interior. So it's thought that where we have the lithosphere asthenosphere system, we have a plate motion moving at the Earth's surface, shearing the mantle asthenosphere below. That these fast directions of the asthenosphere should align with the current day plate motion from that shear. But the lithosphere itself is also seen to hold seismic anisotropy. But instead, that tells us about frozen in anisotropy or frozen in deformation. So it doesn't represent deformation necessarily occurring today, but whenever was the last major episode of deformation to affect that lithosphere. So something like a plate boundary, something like an orogeny that could deform the lithosphere could generate what we call this lattice preferred orientation of the opening. So this is potentially useful in the lithosphere because it tells us something about the history of deformation for the continents. So for Australia, thinking of that system, that plate moving and shearing the mantle, Australia as a continent is one of the fastest moving continents on Earth. On the left, we have an image with GPS vectors. We see very large arrows for Australia moving to the north-northeast at around 8 centimeters per year. And this motion of the Australian continent with its thick cratonic lithosphere is thought to shear that underlying asenosphere in green. We should have flow and deformation aligned to that plate motion. We may get some instabilities, small scale convection, edge-driven convection at the edge of this thick lithosphere, but we'd expect the mantle shear to be very strong in that plate motion direction. And people have seen this for quite a while, looking at azimuthal anisotropy from surface wave studies. Here is from a couple of papers, Weil and Kennett and Yoshizawa and Kennett, looking at radial and azimuthal anisotropy. What we see is at 200 kilometers depth at the base of that thick lithosphere. The black bars indicate the fast direction. We have a lot of bars indicated north-south, aligned with that thick direction. And many other surface wave studies also see beneath Australia. Within the lithosphere itself, however, shallower depths, 100 kilometers, we see different orientations, indicative of this frozen-in anisotropy. So it's thought that we have strong plate motion aligned in the asenosphere, and we have fossilized anisotropy. So what I've been looking at is using a different technique called shear wave splitting. In this case, we have an anisotropic medium, like the upper mantle. We have a shear wave that black enters this medium, becomes polarized into two components, a fast component in blue and a slow component in red. We can measure the orientation of this fast direction and the delay time between them to tell us something about the geometry of seismic anisotropy inside the Earth. And we're often using teleseismic SKS and PKS waves, and these are waves that travel through the body of the Earth. They travel as a P wave in the outer core and then convert to an S wave on the receiver side of the mantle. Because they've traveled as a P wave, they remove any anisotropy from the source side, and they then tell us about anisotropy beneath the receiver. The dashed black in the upper mantle is where we expect our main zone of seismic anisotropy exists. Before we had sort of new deployments in South Australia, I had an honours student, Claire Flashman, look at shear wave splitting with a Bilby array, which was an array of broadband seismometers that crossed Australia from north to south. And what was really exciting there is we found throughout central Australia this predominant east-west fast directions indicated by the red bars on the left and the black bars on the right. And this fast orientation is very similar to the orientation of the gravity anomalies in central Australia, which are some of the most prominent gravity anomalies in Australia, if not the world, that represent offsets in the MOCO at depth. So they align with the gravity anomalies, they align with the general orientation of the tectonic units. But as you go to the north, into the North Australian Craton, they rotate to northwest, southeast, following Tennant-Crete and in layers here. So it's showing a correspondence to the geological history of the continent. We think that it's indicating that not just is the crust deformed in this region, but also the lithosphere is equally deformed in the Proterozoic, in these central Proterozoic suture zones. So we interpret this signature as being a relic, this frozen in lithospheric deformation. But the results seem to be more sensitive to this lithospheric layer and are not sensitive to that plate motion aligned flow in the asthenosphere, or at least they don't appear to be as sensitive. So that was very interesting. We wanted to explore more the Gawler Craton, but this profile is just going through the middle of that cratonic lithosphere. So it's all thick lithosphere in this region. With the deployments of these new arrays over the Gawler Craton, and then including as well for southern Australia, more permanent networks and previous temporary deployments expanded the area. So we now have good coverage over the South Australian Craton, it's pre-Cambrian Australia, but also that transition to the thinner lithosphere, Panaertholic. What we found in this year was splitting there. Again, we pick out this kind of east-west orientation. Now it's slightly more east-northeast. A lot of pink, purple colours of the Gawler Craton. Very consistent across the South Australian Craton. But as you move to the east, over Phanerozoic Australia, the colours represent the fast directions. Okay? Now these splitting vectors are much better aligned with the absolute plate motion, this black arrow. The delay times also appear to be longer. So with this year with splitting and the anisotropy, we think we see a difference between regions with thick lithosphere and regions with thin lithosphere. We compare this now in a lithospheric thickness map. The background colours in blue represent deeper LDBs, thicker lithosphere. The beige colours represent regions of the thinner lithosphere. The colour of the bars now represents the misfit between the fast direction and the absolute plate motion. So in red means they're very similar to the absolute plate motion. In yellow, they're more different. They're different to the absolute plate motion. So we're inferring that where we have thick lithosphere, this is showing us the signature again, this fossilized, frozen in anisotropy. Versus where the lithosphere is thinner, it doesn't contribute to the signal as much, and instead we're seeing that plate motion aligned flow in the asthenosphere. What's really interesting about, if you look more closely at the Gawler Craton, I go back to the geological map of the Gawler Craton. The simplified version here. I've modified this from a paper by hand et al. In 2007. And this was their image with these big black arrows showing this northwest southeast compression back around 1.6 billion years ago. And in the dashed black are some of the major deformation structures that formed in this time, including Calajan shear zone down here where I'm currently working. And in blue are the splitting vectors. And we see a good agreement between the orientation of these deformation structures and the shear splitting anisotropy, as well as some of the background faults in grey. So it's suggesting at this time, which is the last time there was a major deformational event to affect the entire craton, we had a northwest southeast directed compression, which deformed the lithosphere, coherently and widespread. And it was also at the same time that we had the emplacement of volcanics, these red and purple patches, the Hiltava and Gawler range volcanics. So we think that this volcanism, we warmed and weakened the lithosphere, we allowed it to be more conducive to the form. We created this anisotropy that has since been frozen in and preserved since that time. So I'll wrap up here. What we find so far is that the earthquakes appear to localize in this region to a left-lateral fault system, potentially defines better the eastern boundary of the Gawler Craton. Groundwater springs in the area suggest that there's fluid pathways on this fault from the mantle to the surface. We have some new constraints on the sedimentary and crustal structure across the region, with the crust beneath the Lake Eyre basin being thinner than the Gawler Craton, but it's not as thin as we previously thought. And we see strong evidence for coherent frozen in anisotropy across the South Australian Craton. implies that there was widespread deformation of the lithosphere about 1.6 billion years ago, prior to the cratonization of the lithosphere and stabilization, but also happening at the same time as when we had the volcanics, which may be significant. So that's the sum up. Just a heads up that work in the area continues. Currently ongoing is the next deployment called Snaky, which stands for Seismic Network around Kangaroo, Eyre and York Peninsula. So we've got 20 instruments out. They'll be out, come out next year sometime. We'll be using these to, same thing, to learn more about the crustal structure beneath this region, improve our constraints, and also seismicity on the eastern. Work continues. Thank you.
That's the theory. And the work they played. You make a comparison with the gravity, right? Gravity signal. Am I right to think that the gravity signal is mainly from the crust?
Yes.
Yeah.
So it's
but then
mainly interpreted that way.
Yeah. But then those anisotropy measurements.
We think.
Yeah. So do we think that the lithosphere and the crust are exactly the same? Like there's a continuation of to make that comparison? Is that
Yeah, so that's kind of the suggestion. It's suggesting that when we deformed, thought that these east-west line gravity anomalies are uplifted and downlifted blocks of crust. So the deformation that caused that, I think it's not just deformed the lithosphere, but also not just deformed the crust, but also deformed the lithosphere. That there must be some degree of coupling during that event, and that it's preserved not just the crust, but also there's a signature that remains there. So in essence, your question, yeah, gravity is telling us about the crust. Shear splitting is most likely telling us about the lithosphere, and that's suggesting that they've both been deformed by this event. Yes, yeah, that's the interpretation.
The anisotropy, is that related to the alignment of the olivines?
Yes.
And you require 3 component measurements to calculate the direction.
So anisotropy exists if we think of we go back to the crystal. You're right in that anisotropy itself is something which is 3D. So we have a fast direction here, but we have 2 other directions as well. But we can't measure, or it's difficult anyway, to measure the 3D volume of it. So we have different methods which are sensitive to some plane of it. So series splitting was sensitive to the azimuthal anisotropy. In essence, imagine this wave coming in. We're sensitive to velocity variations in this plane. We don't have any information about velocity information that way. So yeah, so we're only getting the kind of 2D slice, if you will, something which is 3D. But we think that in the upper mantle, or plate motions, that most of the shear and our fast direction should be in the horizontal plane, and therefore we're using body waves which have a vertical incident, so they're most sensitive to the plane where we should have this variation.
Is it very computer intensive to calculate those directions, or is it really simple?
If you're trying to do a more computer intensive, when you start trying to do tomography that incorporates anisotropy, now you have a lot more unknowns And the more that you include that, there's more to solve for, more uncertainty.
Ian is asking, can you tell if Australia is being pulled or pushed the northeast?
Not from anisotropy.
It's an interesting question. Do we know actually what's the?
I mean, I go back to I don't know specifically Australia, but I go back to my understanding of plate tectonics, that slab pull is the most dominant force, and most likely, I would think more likely being pulled if the Australia, Antarctica seafloor spreading is passive rather than active. Not an expert on it. Can't tell from this if it's push or pull. We just know that it's in this direction.
Between the South Australian Craton and the North Australian Craton, do we think the Cratons will actually butt up against each other, or will there be thinner, younger crust in between? Do we have any way of telling?
Yeah, so that's kind of what we see here. So this boundary between the north and the south is in this what's called the central Proterozoic suture belt. So we think that when the North and South Australian Cratons fused together, they kind of created this weak zone in here, which was then gone through more deformation cycles of later deformed. This, in terms of the crust, doesn't look particularly the crust is pretty thick in this region. So potentially that having those collisions and sutures has potentially thickened the crust there. What's actually surprising for Australia is Cratons in Western Australia actually have relatively thin crust. So some of the thickest is actually beneath that suture zone between the norms. It's gone through a lot of deformation, so it is potentially a weaker area.
Why doesn't Eastern Australia qualify as a Craton?
Because of the age. So the first of all, the lithosphere is thinner. So you get thick lithosphere where it's older, it's colder for a long time. And I don't have it on this map, the whole geological map of Australia, but the age of the geological provinces here are much younger. So that wouldn't qualify for that. Cratons are really parts, lots of the earth that formed several billion years ago. More than 2 billion. Yes, old cool.
The here in Western Australia isn't particularly thick. That you just said that the West Australian Craton.
Oh, the crust.
Well, that's the crust.
That's the crust.
That's
So
a
this is the
base.
lithosphere.
Okay.
Crust. You would also kind of expect the crust to be, for Cratons, you kind of expect there to be thick crust, but that's more of a crust chemical layer. So I don't know the history of this part as well. I mean, it's still 30 to 40 kilometers thick, which is the average continental crust thickness. But it's not especially thick in crust, but there is thick lithosphere.
An interesting observation. The crust doesn't have to be as thick as the lithosphere. They don't have to get thick or thin together. Okay, I think that's time. Again, thanks everyone.
Thanks for the questions.
No, it's fascinating, yeah.